Good morning, class. Today, we will take up the chapter 6, Structure Analysis. First section is simple truss, the method of joints. Truss method of joints. After this class, students will be able to define a simple truss. B. Determine the forces in members of a simple truss. These two are lecture tasks. First, introduction. Truss is a basic and widely used structure in structural engineering. For example, this is a roof structure. So trusses are commonly used to support a roof. For example, when you go to airport, you can see there are many structure is using those trusses. Trusses are also used in variety of structures like rocket-emitting frame, bridges, cranes, and various tower frames. Here is a bridge structure, truss structure, and this is a crane. Also, this is a crane. And other structure using truss. The advantage of truss structure. 1. Truss structure is light in weight and can be mounted in working site, so it is cheap and easily transported. 2. Member forces in truss are usually actually loaded. The excellent performance of material in tension and compression is fully utilized. So these are two advantages of truss structure. Now there are two questions here. For a given truss geometry and load, how can we determine the forces in the truss members? And for a given load, how can we design the truss geometry to minimize cost? To answer these two questions, we should first know about the truss structure and how to solve for the member forces. After that, we can answer these two questions very well. Okay, first, 6.1, description of a truss. Here is a roof truss. A truss is a structure composed of slender members joined at their ends. There are several kinds of connection forms at a joint. First, form A, members bolted at the joint. B, members pinned at the joint. Before we introduce the method of joints, we must reduce the structure and the load to certain simple model. One, geometric property. How is a simple truss formed? The simplest stable and rigid form of a truss is a triangle. So this is a triangle ABC with three members to form a basic triangle structure. A simple truss is constructed this way, starting with a basic triangle element, and adding one joint will increase two members. For example, here, adding one joint D will increase two members, AD and BD. So use this way, we can extend to a simple truss. 2. Loading property. How do purlins or floor beams transmit loads to trusses? A. Roof truss. The purlin here is purlin, DD prime is purlin. The purlin transmits the roof load to the trusses at joints. That means the purlin DD prime will transmit the roof load through D and D prime, these two joints. B. Bridge truss. Here is a bridge truss. Load on the deck is first transmitted to the stringer. This is stringer. Then to the floor beams. This is a floor beam. And finally to the joints A, B, C, and D of the two supporting trusses. So in the two sides, there are two trusses which compose the bridge structure. So from these two examples, we can see that all loadings act at the joints and they are in the truss plane. That means all the external forces will, through those joints, act the load to the structure. And also this external loads form a coplanar force system. All the forces act in the truss plane. This is a bridge truss. Likewise, all the loads are acted through joints to the truss plane. Okay? Now the second section, 6.2, simple planar truss. This is a model. After the analysis of the geometric property and the load property, now we can form the simple ideal model for the truss. Model of structure, simple planar truss assumptions. There are several assumptions. First, all loadings are applied at joints. This we have already discussed. 2. Members are straight and joined together by smooth pins. So they are connected at joint by smooth pin. That means there are no friction. 3. If straight members are bolted or welded at joint, actual lines of the members should be concurrent. So if the members are bolted or welded, we assume the actual lines of member are concurrent. They have the intersection at the same point. 4. neglect the weight of members, or the weight of a member can be assigned to both ends equally. So this is our method to simplify the weight of a member. You can either neglect the weight or you consider the weight, but they are loaded at both ends equally. Now here's the model of force. Just now we've already discussed for the entire truss. First, we can see at each joint there are concurrent force system because each member acts as a two-force member. So the force in the member is actually acted along the axis of members. So they concurrent at the joint. So the first concept is that at each joint we encountered a concurrent force system. The second concept is that for entire truss, the forces are coplanar force system. Section 3, method of joints. Begin with a simple example through which we demonstrate the method of joints and the procedure. Here is an example. Given external force is P equal to 500 Newton, horizontally acted at B. The other dimensions are shown in the figure. Now please find the forces in each member of the truss. Use this example, we can introduce the procedure of the method of joints. Procedure for solving problems. First, draw a free body diagram of the entire truss and determine all the support reactions using the equations of equilibrium. Solve for support reactions. This is the first step. Now let's draw the free body diagram. At A we have two components, unknown support reactions. At C there are only one vertical component, Cy. So using the equilibrium equations for the entire truss, we can determine these three unknown support reaction components. Second step, selecting a joint with one or two unknowns, e.g. B. Draw the free body diagram of the joint. So now take B as the object of study. Draw free body diagram. It's like this. So now we assume the FBA is in tension and FBC is in compression. This is assumed by inspection. So you can determine the direction of forces by inspection, or you may also assume all members are in tension for those complicated cases. Step 3. Apply the scalar equations of equilibrium for joint B. Sigma fx equals to 0 and sigma fy equals to 0 to determine the unknowns. If the answer is positive, then the assumed direction is correct. Otherwise, the real direction is opposite to the assumed direction. Step 4. Repeat steps 2 and 3 at each joint successively until all the required forces are determined. For example, here, the next joint is C. So for C, we draw the free body diagram and apply the two equations of equilibrium at C. Then finally, we can solve for FCA. So repeat steps 2 and 3. We can finally get all the answers, all the unknowns. Now let's come to a real examples. Here is a very simple example. Determine the force in each member of the truss in terms of the load P, and state if the members are in compression or tension. So in this example, the external load is P, acted at D, and the dimensions are shown in the figure. According to the procedures we have just discussed, we can follow this procedure. Plan. Every joint has more than 2 unknowns. So we have to solve for support reactions for the entire truss first, then apply method of joints to solve for forces in each member. Solution. First, for the entire truss, draw free body diagram. So here at A, we have 2 unknowns components. At C, only 1 vertical component. So solve for entire truss, we can get the final result. Write equations of equilibrium. First, write the moment equation about A. Sigma MA equals to 0. Here FC times 2A minus P times A, negative 1, and which is that to be 0. And finally, we can get FC equals to half P. And then write the projection equation Fx equals to 0, sigma Fx equals to 0. We can get Fax equals to 0. Then the second projection equation, sigma Fy equals to 0. And Fay plus Fc minus P equals to 0. Then we get Fay equals to half P. It's very interesting. The two answers are the same. Fay equals to Fc. Why we get this very coincident result? Why are the two support reactions the same? In this case, the structure is symmetrical, and the active load is also symmetrical. So the support reactions are also symmetrical. So there are some nature property inside this structure, the symmetry. So we can also conclude the general principle of symmetry in structural mechanics will predict that the internal force of members in this case are also symmetrical. So we just use this principle. We can get the conclusion. FCD will be also equal to FAD. And FCB is also equal to FAB. So this is the result of symmetry. Both the external forces and the internal forces are equal correspondingly. So this will save us many effort. Now let's use the method of joint. First, we take A as the joint of study. Draw the free body diagram of A. We assume FAB and FAD like this, and use the equation of equilibrium at A. Sigma Fx equals to 0, then we get the projection equation. Use the second projection equation, sigma Fy equals to 0, then we get this equation. Solve the two equations simultaneously. Finally, we can get FAD equals to 0.687 P in tension. And use the symmetry, we can get this answer. FAB is equal. Oh no, this is the second solution. FAB equals to 0.943 P in compression. These two answers are using the simultaneous equations. Now we can use the symmetry. We use symmetry. FCD equals to FAD and FCB equals to FAB. We get another two unknowns. Up to now, we only left one unknowns. That is FBD. We should solve FBD next step. So in order to solve for FBD, we take D as the joint of study. Then write the equilibrium equations. Draw the free body diagram at D. Here only one unknown, FDB. The other two have already been solved. Write the equation of projection along y direction. Sigma Fy equals to 0. Then we get this equation. Finally, we get FDB equals to 1.33 P in tension. So far, we have solved all the unknowns. So this is the method of joint. That's all for this class. Now let's have a summary. Let's give a summary here. We learned how to solve member forces of truss by a method of joints. The method is based on the equilibrium of planar concurrent force system at each joint. The member forces are solved joint by joint, so this method is suitable for solve forces of all members. This is the first method of solving member force. And there are another method called the method of section. We will learn it next time. So that's all for this class. This is homework. Thank you.